And it's rolling. Alright, we're going to pause for now. Alright, here we are with the first order circuits. And this is our first circuit example we have here. Now, what we're going to do is, since the first one is an inductor, we're going to briefly go over some inductor rules. A rule is that as an inductor reaches a steady state, a state in which the current is now constant, because as time passes, if this is introduced to a current source, say you just added this current source to this inductor, it's going to resist that change until it's finally going to be at 3 amps fully. And when it finally reaches that point, it's just going to be short-circuited, like so. And if you take an ODE, you'll write as a function as this changes over time as it gets full with an e to the negative t, whatever that ends up being, like an ODE. Actually, no. Yes. No, yeah, you will. Sort of. Anyways, what you're going to be doing is that you wouldn't use. That's usually written for decay. So when you have an inductor, we'll use this example. You have an inductor with a resistor. This is called the dampening factor. That's what resistors do. They take stuff out of the circuit. And you'll write an equation with e to the negative t or whatever divided by tau, whatever that is. We'll go into what tau really is in a second. And that will show you what is happening to the current as time passes. So, let's just start doing the problem. Alright, so we have a circuit here. Well, we must first note, this is what I like to do with all my circuits, we must look at the switch before and after the switch is, flipped. Before and after it's flipped. So I am going to write a few different circuits for each scenario. So we're going to make this circuit the circuit before that switch is flipped. So see the arrow indicated that direction. When t is equal to 0, it's going to close. So before it's closed, this is going to be open. So this will be t before 0. This is what this is going to represent. The time before 0. Okay. Now, we're going to assume that this circuit has sat for a very long time before the switch has flipped. That is how most of your questions will go. So, since this circuit has sat for a very long time, we're going to replace this inductor with a short circuit. Since the current through everywhere should be equal, or constant at this point, a steady state, it shouldn't be changing over time anymore. Okay, so what we want to figure out is what is this current, we'll call it IL or something. What is the current through that inductor area where we had short-circuited it? Because that's going to be, we're going to use that value for later in this problem when that switch gets flipped back over to determine what is going to happen because when you switch that flip over, this is going to become it's going to close here, and this is going to short this whole left side of this circuit here. Oops, I don't have that eraser on. And it's not going to allow any current from that voltage source on the left to touch that inductor. So, as time passes, that inductor value is going to decrease its current that's going to be stored in it. And they store current, too. That's what they also do. But since this is open, we're going to solve for everything to figure out IL. And we're going to figure what I naught is, too, because that's what the question from the problem I pulled wants to know. Well, obviously there's no current passing through it at all since it's open, so it's going to be 0 amps is equal to I naught there. And we'll say, what is IL minus the left? This is for the left side of 0. All numbers less than 0. So let's figure out what IL is. So 200 and 100 are in series. These are in series, which is in parallel with that 300 ohm. So let's rewrite that. So we got that 50, and then that's all going to replace a single circuit, which I didn't calculate the value yet, but we'll get to that. All right, let's figure out what that value is. Let me grab my calculator. And that number we get is 150 ohms. Nice. Okay. So, excuse me. All right, so these are in series. So we'll get total resistance as 200, 25 over 200. That'll give us the initial current going through. 0.125. Okay. And now we have some current division going on here. So what we're going to do, we're going to set up as the ratio of the opposite. Well, they're both equal, so it doesn't matter. Total resistance on the bottom times the incoming current. And that's going to give us 0.0625, aka 62.5 milliamps. And that's going to be our IL to the left of 0. And another thing to note, current through an inductor is continuous. And what does that really mean? It means that on the left side of 0 and on the right side of 0, this value will be constant. It'll be the same. Voltage is not continuous from the left and right of 0 for a inductor. And the opposite rules apply to a capacitor. Capacitors are continuous with their voltage from the left and right of 0, and they are not continuous with their current. They're instantaneous. Inductors are instantaneous with their voltage. There will be a few examples I think I'm going to be going over that show that. Okay, so now that we've figured out our initial current through the inductor, if you take in differential equations, this value is going to be our initial. It'll be basically our I of 0, right? If you have your IVPs and whatnot, that is going to be our I naught, our initial starting point. So if we were to, let's say, end up solving for a system of equations, like you have your C1 e to the negative t plus C2, right? At I0, it'll be equal to 62.5. So, and then this would be your I of t, which is I0. You can plug in 0 to solve for your C1, your constants. And then if you have like a second order circuit, you'll end up with, this is like a little brief example, di dt is what you want to find. And that'll let you solve for your second row and whatnot. So we're not going to go that deep just yet. I'm just rambling on some information that might be useful later on. So what we're going to do now is we're going to look at the problems that we need to solve. I'm not logged in. Now I am logged in. Okay. So we figured out a lot of things. Now let's start looking at the circuit as it gets closed. Since what the main goal usually is on the left side of 0, you want to figure out what the initial current is through that inductor. That's your first step. Usually when it comes to first order circuits, well, it is. It is your first step. And then we're going to solve for 0 after the point, which is going to be our transient state, when the inductor value will be constantly changing since now uh, it's not being supplied by that voltage source anymore, because no voltage is passing to that right side, because if you were to do nodal, this whole thing will be grounded. And that means that it's just going to go there. So really you have two separate circuits, this one and the one on the left. So let us figure out what, let's do like a little nodal, let's figure out what the equation is going to be that we're going to write for the transient state I of t as this inductor goes through time. So we can do we'll do a KVL, Kirchhoff's voltage law, here. So we know that voltage for a resistor is equal to R times I, and the voltage across a inductor is written as I, or no, my bad, L di dt. That's equal to voltage with respect to time for an inductor. And that is all we need. This is equal to 0. Alright, KVL. KVL rules. So now we're going to set it up as di dt plus, maybe this might look familiar to you, divide the L, R over Li. That looks oddly familiar. Alright. Now we can do our little differential equation stuff. Let's let I equal to e to the mt. Okay, so this is just going to be m to the first power. If you remember a differential equation, plus r over L. M is going to be equal to negative r over L. So we're going to have an exponent with e to the negative r over L t, or as your book has it as, they do the reciprocal of this so it looks nice and neat, this L over r, and they'll do it as e to the negative t divided by tau, right? Time constant, tau's being introduced, and they let this equal to tau. And that's why it's divided, so you can get back to that r over L scenario. So this will be that is going to be equal to our I as a function of time. Now, let's not forget what I had said earlier. You have C1 here, right? Well, what is our C1 going to be? Well, at I of 0, when I is 0, this whole top up here, when t is equal to 0, 0 times r over L is going to be 0. So you're just going to have Z1 is equal to I naught, our initial condition, which is 62.5 milliamps. So we have 62.5 milliamps. And we won't put it on that side. We'll do e to the negative r over L times t. Keep that all in milliamps. And this is our function, or dampening formula as time passes. And R over L, you can plug in those values. The resistor seen by that inductor is what R is. and it's only going to be 200. So it's going to be 200 divided by 50 millihenries. 200 divided by 50 millihenries, 0.05 decicentimilli. It's 10 to the negative 3. 200. Yep, I get 4,000. So your final answer should be 62.5 e to the negative 4,000 T milliamps. Okay, and that's going to be our I as a function of time. I of t was what we're going to call it. Looks a little messy up there, but anyhow. Now, let's write a formula because I think one of the questions asks, what is I of 0 to the right? What is I of 0 to the right? So, what is I 0 for 0 plus, right? So at 0 plus, we still have this current right here equal to 62.5. So, we know that I naught for this new circuit is going to be 300 in parallel with that 100 ohm resistor. We have to figure out what I naught is for this new circuit. It's going to be let's do this on a whole new blank side. Let's figure out what I naught is for the right of 0. And it asks that right here. It's your part C. We'll explain that. So let's figure out what I naught is in terms of, I'll explain this with a drawing. Okay, so as I said, these circuits are like two different parts, 100, 300, and we needed to figure out what this new I of 0 is going to be, since that's what it wants from the problem. So the 100 and 300 are in parallel, so 1 divided by 100 plus 1 divided by 300. The reciprocal, we get 75. That'll be in series with the 50. We get 125, and 25 divided by 125 is 0.2. So we have 0.2 amps coming in. So let's do current division. Opposite to the one we want, 300 a pop, divided by total on the bottom, times 0.2. We get 0.15, or 150 milliamps. Okay, so that's what's coming in through the circuit at this moment. Now, we also have this current running through here and up here, which will be opposing I naught. From the inductor. So, Actually, let me do it more visually like this. This will be better. So since we know that this 100 ohm down here, not point, let's do it here. This arrow is 150, right? Milliamps, as I had just found. Let's find the current going down here as I naught. And we know the current coming through here initially, when we start out, is going to be 62.5 milliamps. And we could move that back to being over here. So let's do a KCL at this point. So we have this current coming in, this one over here, and this one down. So this one we know is 150. It's coming into the point, negative 150 plus 62.5 plus I naught is equal to 0. Add these together, we get negative 87 plus that over here, we'll get 87.5 milliamps is equal to I naught. And this will be equal to 0, the 0 plus of for this. Now, how do we write I plus or I of 0 as it goes to infinity? Well, as it goes to infinity, 62.5 will approach 0 because as this inductor continually goes, it's going to go to 0 because that resistor is going to take or dampen all of the current out of this inductor. So its final state for I of 0 as it goes to infinity will be 150 milliamps. Okay, and this is just the function we had found for the inductor. V sub L. The voltage across the inductor. So, when we first started off, let me explain that. Where's our first one we did? Shoot. Well, for this one, V sub L, what's the voltage across this inductor here? Well, this is all ground, so we know that the voltage is 0. That's why the 0 minus is equal to 0 volts for that inductor. And then we'll see that it immediately jumps to a negative 12.5. And let's figure that out here. Let's define the voltage to the right of 0 for the inductor. So let's move right here. Okay. So we have this function that we made earlier, which is right here, 62.5 e to the negative 4000 t ma is equal to I as a function of time. I is a function of time. So how do we get to voltage? Well, we can actually turn this expression into a voltage of time, because what we know is that I is equal to L di dt, my bad, voltage voltage with respect to time. So we know that the first derivative of this I of t times the inductor, as written in this equation up top, is equal to V, or voltage, with respect to time. Now let's grab that first derivative. It's going to be negative 4,000 times 62, 2.5. So we're going to have negative 250,000. That's going to be multiplied by the inductance, which is 0.05. So we're going to get negative 12,500. Now remember we had milli here, so we're going to go 1, 2, 3. So we're going to have negative 12.5 e to the negative 4,000 t is equal to voltage with respect to time now. See, this is for the across the inductor. This is also across the inductor. So now that we're here, what do we see when t is equal to 0? Negative 12.5. Wow, that's so convenient. That's the number we need. So, as you can see, the voltage across the inductor is instantaneous. It is 0 up here, but it jumps immediately when you go to 0 plus. And as it goes to infinity, obviously, it's going to be completely discharged. And we can see the expression written for the voltage with respect to time, how we got it. And now let's write a function of t as for its transient state, which it just wants to know what is I of 0 here as time passes. So we know that what we had written before. We'll do a KCL like we did up top. Instead of just doing for the right of 0, we're going to do it as time passes. So negative 150 KCL is the current coming in here. We want to solve for the one going down. Plus, we have this one going this way, which is I of t. We're going to write our function that we have. 62.5. This is all milliamps, by the way. E to the negative 4,000. T milliamps plus I0. We're going to subtract that over. Negative I0. Distribute that negative. We'll have 150 minus 62.5 e to the negative 4,000 t milliamps is equal to I naught. We distribute that here and here. And we got our function as I of 0 as time passes forward for 0 plus. And that's right there. Okay. So that's question 1. Now let's do the next one. Put a marker here. So let's draw this one up really quick. Okay, and now I am recording this the next day over. This is for, we're going to do the second question. Ooh, didn't mean to do that. Let's quickly pull up first order. Second question. Okay, now let's draw this circuit that we're given really quick. Let me draw it real fast. Alright, so this is going to be our circuit that we're going to start with for this second problem. We have two sets of inductors, two resistors. Okay. Now, let's see. We need to figure out what is the equivalent current from A to B. Okay. So from A to B, We need to find the values from A to B after it is short-circuited. And this is going to be right after. Okay, so before we start doing all that, we need to start figuring out these initial values for the currents for these inductors. Because when we start to do or solve for certain things like the short-circuited value, let me draw something really quick to visually demonstrate. So when it's short-circuited, right, this voltage source that's applying it, it's only going to travel from here to here to here. It's going to stay in here because if you were to ground this whole bottom here, it's connect this bottom to ground. This whole part is going to be ground, and this is all going to be ground. So let's first solve these initial values. Okay, so we know that if inductors sit for a while, they act like a short circuit. So we need to first find the initial current coming through here. We can do that by combining these resistors in parallel, and then making them in series with this resistor over here. That equivalent resistance is going to be 1 over 12 plus 1 over 60. It's going to be 11. 176 divided by 11. It's going to be 16 amps. Then we're going to define each current here and here. I1. To find I1, we're going to do 60 over 12 plus 60 times 16. Give us I1. We get 13.33. And we're going to do 12 over 72 times 16. And we get 2.66 amps here. Okay. 2.66 plus 13. Yeah, that adds up. Yeah, okay. So we got 13.33. So this is, we're going to call this I2. Okay. Now we figured out the initial values. Now we know this. Now we have this new circuit once it's shorted. So we know that these are going to be this this one's going to have an initial value of 13.33 amps. This one's going to have 2.33 amps. They're both going to go this direction. They're both going to converge to here, and we're going to get 16 amps again. Right? Then we have this new circuit on the left, which is just going to be 176 amps. So really, if we want to solve for the equivalent current from A to B going down, which that's what it's going to be, we can say that the current up here is 16 amps, because we know that these two put together is going to be 16. And we can do like a little KCL up here at the A node. So it's going to be negative 176. I'm going to call this I0 plus 16 plus I0. These together, we get I0 is equal to 160. Okay, now that we've figured out what IO is going to be, and this is going to be, we'll say, 0 plus, 0 minus will be before that short circuit is added. We'll say to the right of 0, IO is going to be 160, or from A to B. And then as this goes to infinity, as time passes, there's going to be nothing being supplied from those inductors over there. So there's going to be no current going against that this original circuit that we're talking about over here. So we're just going to go to 176 amps will be A to B final, or as it goes to infinity. Right. So now we need to figure out we need to figure and determine how we will solve for this circuit when these two, across these 2 points, right? We start with 176, 176 amps, and then we have 16 amps originally coming in from these two inductors. And then initially from 0 plus we found that we start at 160. We need to figure out as time passes, when will this become 168 amps? Or when will this 16 become 8? Because 176 minus 8 will give us 168 amps. So we need to figure out the transient state for these inductors, how to determine the values of the current as time passes on. So we can combine these in parallel and these resistors in parallel to get a single inductor and single resistor. So if we do that, we will get a single resistor with 1.764 millihenries in parallel with a 10, or no, in series with a 10 ohm resistor. Okay, so now that we have a resistor in our single inductor, let's write our equation. So we know from previous formulas that E is going to be to the negative T, and we know that we start with 16 divided by tau. And what is tau? Tau is going to be L divided by R. So 0.001764 divided by 10. And then we're going to divide that by 1 divided by that number to get a nice little thing going on. E to the negative 5,605.7 T times 16. And we're going to set that equal to 8. No. Yes, 8. Because at 8 amps is when we'll get 168. So 8 divided by 16. Then take the natural log of both sides, and then divide that by negative 5,665.7 equal to T. So let's take the natural log, 0.5, divided by negative 5,665.7, and we get 122 microseconds. Or we could round that to 123, possibly. Okay, and that concludes number 2. Okay, and now we're here with the third and final problem. Okay, so let's see what circuit we're given. We're given a capacitor and a resistor. Okay, and we're given the values for V as a function of time and our I as a function of time. Okay. So, from what we know about circuits with capacitor and a resistor as a first order circuit, tau will be equal to R times C, right? And the formula is going to be e to the negative t divided by tau, right? And R 100, this will be for voltage as a function of time if we pull it from the first one, V, that's given, voltage is a function of time. And our tau is going to be equal, set tau equal to, we're going to set it equal to, okay, we're going to set up tau as shown, because tau is being divided up here. So 1 divided by tau is equal to RC, and the reciprocal of the other side is going to be tau, if you were to do it as such. Okay, we're going to grab the reciprocal 1 over RC. Okay, and that's going to be equal to negative 1,000. Okay, so, and we know that the other equation, if we look at these two equations, we see that the voltage and I as functions of times are given, and that if we were to set t equal to 0, our starting voltage will be 100 volts, and our starting current will be 5 amps, milliamps. So, 100 divided by 5 will give us 20 kilo ohms. That's our resistor value. Let's figure out the value of the capacitor now. So, to continue on with our problem, we have negative 1 over RC is equal to negative 1,000, right? And how we got that is instead of thinking of that as tau, if you were to plug in a value, it's going to be 1 over RC, right? And what the problems like to do is they like to put tau, and tau ends up being equal to RC, right? Which, if you were to pull out the tau, it would be 1 over tau times t negative, right? Which tau is equal to RC, and you get 1 over negative RC. So, we're going to set up as shown. We know R now. We're going to multiply that over. So what's negative 1,000 times negative 20,000? We get a big number. We're going to get 20 million is equal to 1 over C. And we're going to grab the reciprocal of both sides. And we'll go C is equal to 5 times 10 to the negative 8. That is our capacitance value. Okay. Now let's figure out find tau in milliseconds. So let's figure out what tau is. So since we know that tau is equal to RC, let's plug in those values. Tau is equal to RC. R is 20,000. C is right here. Multiply those together and we're going to get 0.001, which is going to be 1 millisecond. Okay. Now let's find the initial energy stored in the capacitor. And the formula for that is simply as given 1/2 capacitance times voltage squared. We know that the initial value of voltage is going to be 100 volts. So you just plug and chug with this one. It's going to be 5 times 10 to the negative 8 times 100 squared divided by 2. And then you'll get as follows, 0.00025 or 0.25 millijoules. And then for this last problem, we need to figure out how much time has passed for 80% of the initial energy stored in, wait, never mind. How much time does it take for 80 to dissipate 80% of the initial value stored in the capacitor? Well, for 80% of it to disappear, you're going to be left with only 20% left of that energy left in that capacitor. So we start with this, right? So it's going to be that number times zero point 0.2, and that's going to be 0.00025 times zero point 0.2. We get 5 times 10 to the negative fifth is going to be equal to 1 half C V squared. And we're going to solve for V because we don't know the voltage. That's going to be our unknown. And then we're going to plug V that we find back into our original equation of 100 or 100 e to the negative 1000 t, and we're going to plug it into into our voltage value to solve for t time. Okay, so let's figure what all that is. 5 times 10 is raised to the negative fifth times 2. Divide the capacitance over. And we get 44.72 volts. Okay, we're going to set the equation on the right equal to that. See what we get. So we're going to do 4.72 is equal to 100 e to the negative 1000 t. 4.72 divided by 100. Take the natural log of both sides. Then divide by negative 1000. And we get 0.804 milliseconds. That will conclude our problems. Okay, just to put that in steps, it's going to be 44.72 divided by 100. Grab the natural log of this number, and then we're going to divide that by negative 1000. And that'll give us t, the time we want. Okay. It's kind of weird to how they use tau, even though what if you were to write this as such, it'd be just that's what this function is, times t, and they just let RC equal tau, and then it just becomes t divided by tau. That's what they do. So yeah, that sums that all up, and that's it. That's all the questions done.